Okay, welcome everyone. Welcome YouTube to the next Water, Wetlands and Watersheds seminar. I think we're getting there. And yes, please, the lights would be great. Thank you. All right, here we go. We are live. So it is, I'll put the lights on just for a minute so we can see this guy here. So it is my great honor and pleasure to introduce our speaker for this week. It's Dr. Jim Jowett. So who here has taken a class with Dr. Jowett before? Yeah. Blows your mind, right? Every time. So actually, I took a class with Dr. Jowett. I took two in maybe 2006, so getting to be almost 20 years ago. And one was in water resources sustainability, where I actually learned sort of much more holistically how water struggles have been a part of human society for a while. I sort of knew that, but very vaguely. And a lot of times we learned about in your class. And it was very narrative, it was very qualitative. And then I took another class with Dr. Jowett, which was contaminant subsurface hydrology, where we had to solve Richard's equation and we're doing all this chemical transport. It's very quantitative. I didn't know I was going to go into this actually. But the idea that that Dr. Jowett, as a scientist, has a very broad scope and a very deep set of thoughts and ideas about how we advance our understanding of water, from the very human all the way down to the spore scale, non-aqueous phase, liquid tar transport, and everywhere in between. So it's a great honor to have you here in seminar again. I won't read this part. Jim works in a lot of ecosystems, aquatic ecosystems across the globe, and also does a lot of teaching at the graduate and undergraduate level, including some experiential learning and what do you call it? Exchange learning or study abroad, that's the one. And so it's been a great pleasure to both learn and work with Dr. Jowett for the past 20-ish years. So yeah, the floor is yours, Jim.
Okay, thank you, David. Thank you for reading the comments I sent you to read.
Let's see, he's the National Academy of Sciences review panel, and he won a bunch of stuff. You'll be able to tell.
We're actually more talk about. And so, yeah, this is a very influential seminar series that we run here, and it's always exciting to be asked to come and talk with this. And I said, what should I talk about? Which of my recent things would be interesting for this audience? And should I talk about a wetland thing or a watershed thing? And I said, instead, I want to talk about the approach that I use and the philosophy, because every paper we write, every time I talk to a funding agency, we get raised eyebrows and some like skepticism of the perspective that we're bringing. And so, well, I'll share our perspective and then I'll illustrate my perspective with examples from water, wetlands, and watersheds, basically until we run out of time and you give me the hook. And so, and so the first one, super brief. Who am I? You can look at, Google Scholar, it says the stuff that I do. You can go to my website and see it says the stuff that I do and the things that we're working on recently, or at least when I last updated it a year ago. You can see the words course that I teach, water resource sustainability, and I also teach another class now, landscape hydrology, which has been quiet for a couple of years. I'm proposing to teach it again in the fall. A little bit contingent on if we get enough students that register for it. What have I been doing instead of that? Past few years, as David mentioned, is I've been teaching the study abroad program, which I copied this off the study abroad website. And so it's full. There's only a wait list. There's not wait list anymore, but it's full for this year, where I take students to Europe. Okay. And you see on my website that I'm the landscape hydrology laboratory, and my class is about water resources and my work is about hydrology, but I added this sort of tagline that I made up of hydrology plus humans to indicate that I'm not working on just hydrology. I'm on minimizing human impacts on ecosystems, but also the broad intersections of humans and hydrology. And that manifests in my teaching as well, as David mentioned. All right, so that's who I am and what I do. And what I want to do today is I've got three sort of intersecting concepts that I want to walk through. The first one is very short and easy. I don't know what color is this.
Light blue, yeah.
So then this first, that's to indicate that's the first one. And the first concept is what types of systems am I interested in? Well, for today, I'll try to give examples of water, wetlands, and watersheds. So that first one was pretty straightforward. This second one, really, I want to talk about modeling, hydrologic modeling. And so this is my conceptual diagram to illustrate a way of thinking about modeling that I subscribe to and I promote. That you don't have to, but I would suggest it's useful. So let's first say, what do we mean by modeling? So I'm giving you a quote from an influential paper from WRR by famous hydrologist Jim Dooge, which, I don't think, because it was a long time ago, kids today, they don't know the famous scientists, right? So it's less about remember the famous old scientists and more that, he wrote this paper, but he's the guy who introduced, hydrographs, by the way, and a lot of other stuff. But he wrote this paper while he was a senator, and he had been a senator for more than 20 years. And he was the minister for Ireland. He was Irish, the minister of foreign affairs. He chaired the Irish Film Board. So it's also, I think, worth celebrating that hydrologists can be influential in a lot of different ways. So here he's writing this paper and he says, look, a model is a system that's simpler than the prototype, that it can reproduce some of the characteristics, but all the characteristics. And then he goes on to say, well, who is modeling and why? Are you interested in a scientific perspective or an engineering perspective? No, I don't necessarily say you have to slice and be one or the other. And that's why he says, or it could be the same person at different times with different perspectives. Might be interested in predictions from a model for checking hypotheses and confirming a theoretical system, to maybe understand what's happening. And an engineer might be interested in the model to make predictions. And he supplied this nice little diagram, which Ronnie Best used to quote this all the time. Ronnie Best used to be the director of Wetlands. So I was very influenced by hearing Ronnie Best say that if you go out and you take samples, you're observing change in the system. And if you want to understand the change, you do experiments, maybe lab experiments, and you're understanding how things change. But if you want to predict the changes, that's where you need models. And then our buddy Jim Dooge is saying, well, okay, which are you modeling to come back and be a scientist and gain better understanding? Or are you modeling to be more of an engineer and control the system? But either way, it's about doing a model to make some predictions. So once I introduce it, I'm going to do some modeling. You now enter the classic, what kind of model, how complex of a model should it be? And everybody, I think, likes to believe that they are at the fulcrum with their approach, right? And I'm at the perfect balance. It's not too complex and it's not too simple, but it's a classical challenge of what is the right level of complexity for your model. So I'm going to introduce a different framework about this. And it's a helpful diagram. This was supposed to come in. Oh, ignore this one. Christoph Niemann is an illustrator, and he is pretty famous for his New Yorker covers and other illustrations, but he's gained quite a lot of renown, such that he's featured in a Netflix documentary about design. I particularly like this one from just 2023 about how AI is going to help you. Looks at the situation. No, like you got these crumble things and does. Okay, so he's an illustrator and he's famous. He's featured in Netflix. That's the idea. And so he introduced this next diagram, which is to me a very influential way of thinking about complexity and communicating a message as a guy who's an illustrator. And how abstract should my illustration be to effectively communicate the message? If you want to illustrate an idea of a heart, maybe Valentine's Day card, and you say, well, this is very abstract, maybe it's too abstract and doesn't quite get the message, and that one's maybe a bit too realistic. And so somewhere in between is the suggested idea of choosing the right balance to get your message across. So that's first of, I got two more. So instead of the fulcrum of the simple and complex, I've got simple models and complex model, but I have this other axis of understanding and what do I learn about the system along the way. And you see that I would maybe start with something very simple when I have limited understanding, and as I gain more and more understanding, I can make a more complex model. And this idea is not super recent. I'm quoting the US Supreme Court Justice from the early 20th century, who's credited with this notion of simplicity on the other side of complexity. And he's writing that, I appreciate simplicity, but it should be on the other side of complexity, but not that which has never defined it. Meaning after you've learned and understood the system, and then you can go to the other side and have a more simple representation. And that's what's illustrated in this diagram, is the simplicity on the other side of complexity. We meaning me, colleagues, and a group of colleagues in Germany. This was a key diagram in our proposal that was funded for 2 million euros, where I explained this. I talked about all of our homes, and my German colleagues, they ate it up. They loved it. And one of them, Ralph Mertz, I don't know if you know of him, he's a pretty famous hydrologist, and it turns out he's also an artist. And so he drew this diagram for our proposal. And then, he inflected a little bit of, populism mixed in there. But it's really talking about how do I model and represent reality, and then I got a simple view, I got a complicated view, and it's too complex to communicate maybe to regulators and stakeholders, and it's too complex to be transferred to other scientists, and this simpler but informed answer. One last one. These are two chefs who have a Michelin-starred restaurant in southern Italy. It's the only restaurant in Italy with more than one Michelin star. And they, Michelin-star restaurant is haute cuisine, expensive, small, weird. And so they had this famous dish, which is like a smoothie, like a foam. I don't know what's in it, but you notice it's a cast of the chef's mouth. And the way, and there's no utensils, the way you eat it, you pick it up and you. And so, right, it's weird. And so the reason I'm telling you about this is because they went viral when a food blogger influencer went, it's a Michelin-star restaurant, you kind of know what you're getting into. And so they posted, and they ripped this place into how pretentious and crazy and expensive, and like you get like 3 molecules of food, and then it's all weird. And so the chef Pellegrino wrote a response, like almost a manifesto of a response. And I'm going to tell you a couple things from his response. And in my mind, he invoked this idea here. And he said, and he pictures himself like a chef, and picture like a artist, like a painter. And he said, if you could draw a man on a horse and it looked like this, you'd be a very good illustrator. All your friends would be impressed. That is very good. That is like if you're a cook and you cook for the family and everyone comes over and they love your cooking and it's very successful. You should be proud. If you could paint a man on a horse that looks like this, that would be in a museum. And the chef, like you would own a restaurant, maybe even a Michelin-starred restaurant. I'll just point out that if you could paint like that, then people might bring their kids to Europe to see paintings like in the museum. Now, Chef Pellegrino, but the museums are filled with paintings like this. Like, I am bored with paintings like this. If you paint a man on a horse that looks like this, you're discovering the unknown. You're breaking new frontiers. And as a chef, he's an artist, not just a cook and not just a chef where you come to get spaghetti and meatballs. So to be able to do this type of modeling, complex models, you have to become an expert. You cannot do the complex models without gaining expertise. And I would suggest that it's only after you've gained that expertise that you could develop new, simpler perspectives and ways. And since it's my presentation, naturally, I would suggest that the visionary label would go over here in the type of reduced complexity models that my group favors and that I advocate for the people that I work with. And the term I used is reduced complexity, meaning it's not just a simple model. We went complex and then we reduced the complexity. That's the big idea from this presentation is about this perspective. So now we'll go back to our intersecting concepts, and I would say, well, where can we apply and see some evidence of this approach? Well, I said, okay, water, wetlands, and watersheds. What about water, wetlands, and watersheds? And so the last concept for me is this hierarchy of disciplines and perspectives about water, watersheds, and wetlands. And to illustrate that, I'll just do a turbo, like a growth and a scientist from myself. Like my master's work was about contaminated groundwater, and for me, it was a water quality problem, and that's the lens that I started. And then as I segued and moved on to PhD, it was, you know what, water quality isn't enough, isn't cut it. It's a hydrology understanding is needed as well. Maybe the exact ratio of those to be determined, but still heavily on water quality. And then when I came back to the UF as a professor, and in my department, there was a lot of wetlands related work, and instead of just groundwater quality, could work on wetlands. And I said, well, it's very similar concepts, but instead of organic contamination, it's now nutrient cycling. So not just water quality, but biogeochemistry. And I got to the point that I felt maybe even kind of smug in the harmony between the water quality, the biogeochemistry, and the hydrology as the perspective that I was teaching and using in my research. But then I said, what do we care about water quality for in the first place? Why are we monitoring and measuring water quality? What does it tell us? And in the wetland context, it was usually something about the ecosystem health. And so I said, I want to also be looking at, we're not trained as ecologists, but the reason you're standing in the wetland is because thinking about the ecosystem. So, okay, this is where I was now in the water, wetlands, and watersheds hierarchy. But then why do we care about the ecosystems? What is is it intrinsically for the protection of ecosystem? Yes, but in a lot of ways, it's that our society is supported by, built upon ecosystem services. And so, now I said, okay, here is my hierarchy and my pyramid of things that I and we should be working on and interested in my group. And lastly, more recently, so if you see the job titles from full professor, then you segue to the guy in the corner office that everyone ignores. Is where you are now. And so I said, well, where does hydrology come from? What's the driving force of hydrology is the climate dynamics? And up until recently, climate change was something that people were interested in, and so I was excited about working on climate change as well. So here's the hierarchy of my last concept of this notion of the intersection of these. And now we shift to a handful of examples. We'll see how many we can squeeze in. I had more than 5. I trimmed it to 5 just to see. That's the maximum that I think anyone would want to listen to. So we'll start with the first one, and it's about my very first paper. And it's not that I came here to tell you about my 20-something-year-old paper. It's that I think that this is an illustration of how I came to this path and what was influential for me that I'd say probably most of the people that I work with don't recognize actually either. And so this is about hydrology and water quality. And so my first paper, when I was a grad student, I did lab experiments. The exact details aren't the story today, but I did these lab experiments, and I did the experiments because, and it was hydrologic, and we had these flow chambers that were sort of this big. It was on a bench top, and it took several days to run them. And the reason I do the experiments is because I didn't know what was going to happen. I didn't know what the outcomes would be. Change the parameters and see what would happen. At the time, there was a numerical model, the most powerful numerical model used in petroleum engineering, subsurface, removing oil from the surface where a lot of money was involved. And so we used that. It's from the University of Texas. So we used that very powerful model. I had a visitor from Texas come and show us how to use it. And so you see what I'm showing in this one is a simple experiment where there's no real chemical reactions. And then this one where it was a bit more sophisticated experiment. And I was able to get the model to reproduce experiments. So, okay, felt pretty good about that. But the reason that was very helpful is it both allowed me to science engineer diagram, understand the processes, but also to make predictions about future conditions. And so I show you these to say, now I didn't have to run new experiments. So I was like a total convert. I spent all this time doing experiments. And if I change the parameters, what's going to happen? I could run the model and see what's going to happen. So I could learn a lot from the model. So I said, okay, well, not just I'm now a modeler, but to do experiments and couple it with modeling, I felt like you'd learn a lot. All right, so now we'll go forward to my PhD research. This is a few years later. You notice it in the paper. And we've got laboratory experiments where we're trying to figure out ways to clean up contaminated aquifers. And we do lab experiments where we flush solvents through contaminated soil, we flush surfactants through contaminated soil. And then critically, we scaled up when we did field scale experiments at real contaminated sites. And lab experiments took a few days. The field experiments took weeks to months. And to run the complicated, best model in the world, to become an expert, I was an expert at using that model. But the field sites were very complicated, our contaminants were complicated, our chemical mixtures were complicated, it was very dynamic. It was a huge challenge. We were going to multiple different field sites to set up the model for all that. And I was like, it is an overwhelming problem to try to model these. And is it really going to tell me what I want to know? And that's when I went on the other side of the complexity. And I said, can we do this with a simpler model? And so this paper, these are the key insights to reduce the chemistry of how the solvents work and the chemistry of how the surfactants work, and able to capture the different phenomena of how the solvents dissolve the contaminants versus how the surfactants emulsify the contaminants with a simple framework. And I don't want to totally be lying to you. You see, this is equation 34. So it's built on a fair bit of, let's say, expertness to develop and say, and then here's the equations, and then we can condense, we can simplify, and we can come up with a simple approach. And so, okay, we can reproduce, we can understand what was driving it. And then lastly, we had non-equilibrium dissolution where it was rate limited. And because now I had a predictive model, I was able to say, well, what if I had done these experiments at a different velocity? If I had changed the flow rate, because I had a predictive model, I could now say, well, what if I wanted to do it differently? And so these curves here are showing this is the real data that was at non-equilibrium conditions. And if I had done it slower, I would have gotten the contaminants out with, this is a dimensionless time. So slower means maybe a longer time, but with less use of the solvents that we use. That message is less important than the idea that now I could make a prediction with a simple model that I was able to transfer from lab to field, different types of solvents versus surfactants, and different types of field sites, because I had made it a tool that was simple enough to use and transfer. So I said my first example was from back in the day, and it was less critical that we know all the insights that we learn and more about the experiments and more about the perspective. And to say that, you know, I now was sort of a convert. First, I was a convert to the power of modeling coupled with experiments. Then I was a convert to the simplicity on the other side of complexity. So here's now a more recent one. We jumped to 2022. And classic problem in hydrology is the rainfall is partitioned into runoff. Remember, we've dropped water quality in hydrology and climate in our hierarchy. Rainfall is partitioned into runoff and evapotranspiration. How much goes to runoff? How much goes to, that's the big question in hydrology, it has been for decades. And we know, and has been a conjecture of established for a long time, that at a given site, the average evapotranspiration is a function of the rainfall and the potential evaporation, the thirst of the air. And here I'm showing the spatial pattern of runoff around the world. And so what controls this? Well, it's these things that control this, but critically, what is the function? that control the zones. So since 1974, there has been a long-standing empirical equation that's been used to describe it, Budico equation. And it's empirical because Budico, and subsequent investigators took measured data of runoff from catchments and plotted it on this sort of dimensionless plot where this is the rainfall divided by the potential evapotranspiration, and this is the evaporation divided by the potential evapotranspiration. So it's a dimensionless index, and then these dots indicate like measured data, and then that blue line is just a best fit. A curve like this goes through the data, so I think it should be something like this, and it's been that way for many decades. And then a couple decades later, a very nice, simple looking equation was introduced, and there's been hundreds of papers deriving that, using that equation, and we would call this the parametric Budico curve, because it's the same thing, but it has a parameter in there, n. And you would say there's a benefit of this equation instead of the blue line. What about these black points down here that are far from why are they far from the blue line? Because there's some characteristic of that watershed that makes that one different from the average trend. And so these dashed lines are that lower equation with different n values. And so Nathan Reaver and Dave Kaplan and I, we looked at these data and said, yeah, I don't know about this catchment property thing. And so what Nathan did that was very creative is he took long-term data where over time the climate had maybe changed or variable, so different climate properties. And if this was a real phenomenon, then as the climate changed and there's a catchment characteristic that causes this, then the idea was that the curves, and we weren't the people that published that this should be, because people were saying, oh, look, it's awesome, you can use this curve to understand climate change. The climate changes and we can make a prediction. And so what Nathan says, that's no, man, these curves of the real data are like the opposite direction of this curve that all you guys are using. So we said, well, what is it? And so, Nathan's big sort of insight was to say that this equation is the annual average, and intra-annually, the seasonal patterns of the rainfall and potential ET is maybe the difference into what causes this. And so I'm illustrating with real data from many different cities around. This is real climate data from the climate research unit in England. The blue is rainfall, the red is potential ET, and the intra-annual pattern, what we call the asynchrony between these two sort of sinusoidal phenomenon, have different phase, different overlap, different amplitudes, maybe even different means. And so the surplus of the blue minus the red, so I don't know, is this a bluish color here? Mm-hmm. So this is the runoff, where the rain is more than potential ET. And the amount of runoff, the amount of water available to ecosystems, the amount of water available to people is a function of, right, as we have known for decades, of the rainfall and potential ET. And the annual average is a crude approximation, but if I describe the function with two sine waves, and I appropriately account for a couple of annoying things like where the sine wave gets truncated like this, if I do that, I end up with, here's Budico equation, and here's our equation. And so I get this equation, but critically, it has a term where this accounts for the asynchrony between the two sine waves. And we're able to, this is binned by latitude, and this is global runoff data. And we're able to reproduce the global patterns of runoff. What we say for the title of the paper, we're able to explain the global pattern of water availability. And if I take the parameters that describe those sign functions, if I take how asynchronous the rain and potentially ET are different places of the world, when I take the average of all of those and I plot our equation, I get this, and then this is the empirical just fit to the data equation. So we said in our paper, well, what does this one does? It allows us to explain the observations and explain why this equation that people have used for a long time is able to work. Because instead of trying to do a global climate circulation model, we looked at the situation. So what can we do to come at it from a simpler perspective? So we're already up to number 3. This one is very short. This one is actually not published yet. We said the seasonal variability, the rainfall, and potentially T controls the amount of runoff. It also controls the seasonal variability in the runoff. And where does the runoff go? It goes, well, to the coasts and to estuaries. And so we're interested in climate change and how sea level rise will change the ecosystems in estuaries, change the water availability in coastal cities. But really, to understand the sea level rise, you gotta subtract out the regular seasonal variability. And so we wanted to understand the seasonal variability. So I'm showing here is several different global estuaries with the runoff and the salinity in a measurement location in the estuary. And you can see that the salinity patterns are a little bit different in different ones, and the mean salinity is a little bit different in different ones. So what would be the conventional way to understand and attack this? If you were engineer scientist, is you would use a model such as the most well-known one, among the most well-known is Delft 3D. And what you're looking at here is like a finite element mesh of, you would break down the geometry of your study area into grids or mesh elements. You would solve the differential equations in all of those locations. You would gather a lot of data to characterize all of the physical properties of the river and the estuary, and you could make a very powerful, detailed model to be able to predict and explain these things. Or alternatively, you could start with, okay, the mass balance of the inflows and outflows to the estuary as a whole, rather than try to make it as complex as possible. What's the simplest representation we can have? We got to do a few clever things about defining the inflows and outflows greater than 0 or less than 0, but you do a few things in the mass balance and you account for the critical driving forces, which is fundamentally the tides and the river flow. If I account for the tides and the river flow, then I get an equation which you can't get a lot simpler, that the dimensionless salinity is 1 over 1 plus the dimensionless river discharge. Well, it's a little bit of unpacking of what do we mean by the dimensionless river discharge, where it's a function of the tidal range and the river flow in the area of the estuary. And then with this equation, and you get these inputs, then you're able to explain, slash predict. This is the mean absolute error, and we only were able to run Delft 3D in one estuary, got results that are pretty similar. Do this fancy, powerful, awesome model, and you get pretty much the same result with this equation. And then we apply just our simple equation, because to take Delft 3D and apply it to all these estuaries all over the world, that would take like 2 years of an expert modeler to be able to develop and implement and apply that model. And to take our equation, we just gather data and explain it pretty well. We're up to number 4. This one now, in honor of where we are, I made this one a little bit more in depth to talk about wetlands. So first should introduce the idea of the geometry of the wetlands and the hydrology of the wetlands and the water quality in the wetlands and what's the ecosystem functions of the wetlands. Today, I'm not talking about water quality in the wetlands, but the hydrology is not independent of the geometric considerations for wetlands. And it's useful to remember that when we start talking about fractal characteristics, that we could be talking about statistical or geometric, and I'm actually talking about both. For example, in the geometry, the self-similarity is very famous from Benoit Mandelbrot, where this fractal dimension would be like, you would call this for Euclidean geometry, and we would think that the perimeter in the area would be related by this exponent 1/2, because when we say a circle, it looks like this, but of course, when they say the fractal characteristics of the geometry, it's really saying that the perimeter is crenellated and not perfectly smooth. And so we would expect in natural systems that we would probably not expect a lake and wetland or forest boundary to be perfectly smooth. And so we expect the geometry to have some fractal characteristics. Similarly, the statistical character, when you say fractal, what they really mean is a power function with scale invariance. And whereas this would be, let's say, a normal distribution, and this is the probability, it's like a PDF on log scale. And for a power law, it's linear, so the slope doesn't change no matter the scale. I change the scale and the relationship is invariant. That's the big idea with fractal statistical self-similarity. In rivers and catchments and watersheds, this statistical self-similarity is long known. This paper is a whole raft of power functions of fractal behavior of different area, length, flow, the basin widths, the stream lengths, the stream water characteristics, a lot of different things are well recognized to be that, to the extent that two of the most famous watershed hydrologists, Rinaldo Ignacio Rodriguez Turbe, they wrote a book called Fractal River Basins. Rivers, well known. Lakes, about 15 years ago, a whole cottage industry of papers were gathering data on lakes and saying, whoa, lake sizes are power law. And there's a whole bunch of papers that say, wow, it's amazing. And here's a paper that even includes, we looked at asteroid impact depressions on Mars, and the areas of those are also fractal. It's amazing. So our group said, okay, well, what about wetlands? And it's mostly really specifically talking about geographically isolated wetlands rather than, say, riparian wetlands. And well, I just said that, but another type of wetland is the ridge and slough is the precursor to the geographically isolated. This one is again with David Kaplan and a few students, and also with Matt Cohen. And you know, the relevance of this particular case, I showed us one slide on this, but the relevance is like to restore the Everglades and ridge and slough. We see the degradation of the ridge and slough landscape characteristics. So what is the natural configuration supposed to look like? What are the drivers that are causing the degradation? So which knob should we turn in restoring that is causing the degradation? And so we have a series of papers about that. And this particular one is looking at the characteristics and the size distribution of the ridges and the separation distances between them. And the critical thing is that we concluded that they are aperiodic, that there is not one wavelength of separation that is standard, that the distances and the sizes are fractal power function, and that they cover a wide distribution of sizes and separation distances. And so when you think about what are the governing phenomena that lead to that, a test of the hypothesis of does this governing phenomena control this is does that phenomena lead to periodic or aperiodic landscape configurations. This paper wasn't testing those. This was saying this is the thing that you should use as test. We have other papers about that. But it's the idea that instead of getting drowned in the complexity of all of this, if you can reduce it to the statistics of that and extract a key characteristic of the statistics, it can help you understand what's driving the system. In the geometric fractal behavior, I'm looking at isolated wetlands this time. This is probably Matt Cohen's most famous paper. And it's one of my most highly cited papers as well, very influential about isolated wetlands and looking at different patches of landscape around the country and looking at the characteristics of the isolated wetlands. And what I want to call your attention to here is a perimeter area ratio of isolated wetlands in different parts of the country. And you can see that this line here would be as if the wetlands were a circle with fractal dimension 1, and then the real data, not super surprisingly, show that the wetland fractal dimension is greater than 1. I don't think the reason that hundreds of people cite this paper is about this insight, right? It's sort of a hidden gem, one could say, in that paper. But then separately, after this, working with colleagues from Italy and Illinois and Indiana, we tried to go to the same places that Matt had looked at and look at the geometry of isolated wetlands to try to understand the fractal nature of the wetland shapes. And we measured the fractal dimension. We used the NWI, the National Wetland Inventory data, and we compared it to a topographic depression index model that is just based on the DEM and not based on a sort of aerial imagery interpretation of where the wetland is or isn't. And fractal dimension of 1 would mean they're a perfect circle. Fractal dimension of 2 would mean it's a line. And somewhere in between is this crenellated perspective. And notice that the National Wetland Inventory, where they're labeled isolated wetlands. What this indicates to me is that they're actually a riparian wetland, and you mislabeled it. Oh, it's okay, that's fine. This, by the way, I should say, these colors are the study areas, the same ones that is in Matt's paper. And these little dots are from all the isolated wetlands in the United States. So there's 20 million data points there. Notice when you use a topographic depression model, you don't have the riparian wetlands, you just have the isolated wetlands. You've got a few that are down here, who knows what, but the general tendency of the data is around fractal dimension of 1.33, which was actually quite gratifying because Benoit Mandelbrot, in his 1982 famous book that introduced fractals to the world, includes in that what he calls the 4/3 conjecture, that limits the planar geometry of a closed circular shape or a planar shape. It's really called a Brownian random walk, but he used very famously the geometry of islands as like a realistic example for non-abstract math people to think about what he's talking about. But we could say, or the geometry of patches in landscape, like wetlands or lakes or forests, that planar perimeter fractal dimension should be a limit of 4/3. There's a YouTube video of an interview with him. You can see him talking about it in 1998, very proudly, by the way, about this conjecture and how sophisticated it is that 16 years later, no one had proved it. No, we didn't prove it. No one had proved it. And 2 years later, the proof came out. You can find that on the archives, the physics archive, physics journals archive. Good luck trying to understand that paper. I can just say from the title that, and the abstract and all that, that they feel like they proved it. I didn't challenge whether they proved it or not. But the key point is that, he said from empirical observations, it's 4/3. They said from mathematically, it's 4/3. We did 20 million wetlands in the United States, and the fractal dimension of the 20 million wetlands is 4/3. Okay, so good. Is that simple? Well, I would say that you reduce the characteristics of 20 million wetlands to one number. That's extracting some simplicity out of the complexity. Also, the size distributions, of course, are fractal statistically in power functions, which brings me to why are we really interested in these systems? Let me just say, I said lakes, well known. Now you can say, some guys published a bunch of papers saying wetlands are fractal. Now this brings me to what are we interested in? On my hierarchy, we did hydrology, we did water quality, and they really, what can we say about the ecosystems with all of this? And so we said these isolated wetlands are geographically isolated, but they're not hydrological. That's one reason Matt's paper is so famous, because it proposes that they're not isolated, that they're connected hydrologically, biogeochemically, and ecologically. There just wasn't a lot of data at that time. been a cottage industry of people following up and saying how the wetlands are connected to each other. So we were interested in the idea of them being connected for organisms that migrate and use them as habitat. And so as a habitat network, and the idea that the organisms would disperse and migrate between them, so if you could describe the wetlands on the landscape as a network. And we had some papers, we had a couple papers that did that. And then we said, and this is where Andrea Rinaldo came in and helped us out. And, you know, because he's super well versed in all literature, honestly, of all disciplines, but in ecology literature, and came in and said, you know, that it's not like just the population of the organism in one habitat. When you have a fragmented habitat across the landscape, then the population is best described as a meta population. This is, I'm gonna come back to that. And so there's a very famous paper that talks about, not introduces the idea of metapopulation, but introduces a way to quantify the capacity to sustain a metapopulation on a fragmented landscape as a function of the fragmentation characteristics. And they used data from butterflies that they measured on these series of islands and measured the fragmentationness of them. Here's some words describing there's a metapopulation capacity, there's a species parameter, and there's a spatial location of the fragments. And so you get the spatial characteristics of the habitat and you get the species characteristics, and you put it together and you're able to predict the probability of occupation on the landscape. And as I said, very influential paper. The thing about our isolated wetlands is ours, but just like this, fragmented landscape. What kind of organisms would use the wetlands? Well, Dave Boucher with the USGS had just published their data of 20 years of monitoring of amphibians, where they went out every month to a series of wetlands and they counted how many of these frogs are in this wetland. So the occupancy, we have now occupancy data of organisms using wetlands dispersed across the landscape. But the thing about the wetlands compared to the butterfly habitat of, let's say, forests, is the wetlands are highly dynamic. And so, you know, this is not a simplification, this is an extension where they call this a stochastic patch occupancy model. Their famous paper is not going to say there's 6 butterflies in this catchment, in this forest, and there's 3 butterflies in this one. That's a statistical model that's going to say the probability of occupancy of this patch and this patch is about 20% or 80%, and that's what this model was able to do. So a stochastic statistical patch occupancy model, but it's static in time. And for their applications of butterflies and forests, that was fine. But for the wetlands, the dynamic character is really important. So this is basically, that's the model. So it's an extension, but it's not that complicated. You know, it's pairwise combinations and a few parameters, and you unpack it, there's a little bit more underneath the hood there. But really you have to introduce the dynamic character of the patchiness. So we had a few papers to introduce that. We went to the, you know, this is the place with Dave Moucher's data. It's the Cottonwood Lake study area, and there's about 16 wetlands in a 2 square kilometer area. But what's interesting is that these wetlands are embedded in a 400 square kilometer area with thousands of, let's say, similar-ish wetlands. And so, yeah, they only monitored here, well, only decades, right? Month by month, monitoring here, but unknown what's going on out there. If only there was some way we could predict what was going on out there. So that's the motivation for our model. And so I skip over the hydrologic modeling. We used our simple model framework to sort of predict and explain hydrologic variability. And now we have this as an input to our dynamic patch occupancy model. This is Dave Boucher's data of observations of over time and the occupancy of there's frogs there or there's not frogs there. And with our dynamic model of the wetlands changing and growing with the distances between them, and critically, you need to know something about the species. How far do the frogs hop? So you introduce that, and we're able to reasonably reproduce the data. And then if you had the old SPAN model, you would say 40%. That's not bad, that's the average, but the dynamics of that, right now you can just pause and you can guess, what is this useful for? Well, I understand the system better now, scientist, land manager, ecologist, let's say nature conservancy, which wetlands should I buy and protect? Which wetlands should we allow to be developed? Which one, how many do I need is where the reasons why we said we have a model like this. These are our study wetlands. This is the 5,000 wetlands. And what about this? This is the probability distribution of occupancy. But if I took 16 wetlands, any 16 random wetlands, you could have got a probability distribution that looks anything like this. So which 16 wetlands, matters a lot. Last on this, we said, what if the climate changes? What if I lose some fraction of the wetlands? And what if I have both happen? What is the occupancy percent? And so this is just sort of an illustration of the concept for us. And we're sort of, hand it off, hopefully future people find it an interesting way. We'll see. So far, has not caught the world on fire. I've been fielding calls from reporters about that one yet. And so the summary of all that is that you can reduce and you can integrate your understanding of the habitat spatial configuration, the characteristics of the species, and the dynamics of the changing habitat suitability into a unified framework to evaluate what we really fundamentally care about is the persistence of the species.
You'll have to skip number 5.
Yeah.
If that wasn't, yeah.
Let's see. Avert your eyes from how awesome number 5 would have been. So now in closing. In closing, my summary points are not about my examples. My summary points are reminding you, about thinking about your own work and your future life as a scientist, about what's the right level of complexity for what we're trying to achieve. And right, that most complex model requires expert skill to be able to build those models. And it requires more than expert skill to go beyond that and to do the simpler approaches. I was surprised the first time I saw Picasso's early paintings, like when he just do it and shortly after, right? And masterfully depicted. He's not doing abstract art because he's not able to do representational art. Not everyone is gonna like your new ways of seeing and your simplified, and I'm bored with the old ways. A lot of the audience, a lot of maybe the agency staff, maybe some of your colleagues are gonna say, yeah, Kate could have done that. And yeah, but if you transcend beyond just applying the super expert model, then that'll allow you to maybe move and won't be sort of trapped within the hierarchy. That's
All right, thanks, Jen. All right, so it was a whirlwind tour and philosophy and science and engineering. So if you have to run to class, you can. But otherwise, let's have some questions from the room and I'll field any from YouTube. We have a pretty good live streamers here, up to 16 on YouTube. So, all right, so from the room. Yeah, Nick.
No specific hydrology questions, but as far as the abstractometer, where do you put machine learning as far as do you consider it a simplified model or do you consider it a visionary one that is able to make insights?
Yeah, and I'll repeat it for the stream. So the question is, where does Dr. Jowett see machine learning techniques along the abstractometer gradient?
So for me, it's what is your goal? What is your objective? And if your objective includes enhanced understanding, I like the model with fewest parameters that I can identify their controlling behavior on the outputs. That's for me, right? Like as an example, that sign asynchrony one. I can say, is it the phase difference? Is it the amplitude difference? In the future, if the amplitude of potential ET changes, I can explain why I would predict a change in. So it's like as a parameter that I have a mechanistic like explanation of what it does. So if my goal is to have an understanding and even transcend to use that understanding to make a prediction, then a black box where what happens is something that I can't explain and don't understand would not be my first choice.
So he doesn't even graph it. He doesn't even put, no, that it's in a sense, it's too abstract, even though it's complex, right? Because it has, it's under the hood, very complex, billions of parameters maybe, but it's abstract in the sense.
Or maybe it's too realistic. It's either, it's maybe it's a circle and not a line, right? Because the same could say, like, instead of machine learning, I've got a mechanistic model with 1 million parameters, and I've described every part of the estuary. What's the roughness, spatial pattern of the roughness and the vegetation? Or maybe you do have a vegetation pattern, and maybe you got some, what's the sediment permeability everywhere? And so there's a lot of things that you don't really know, but you put in the model. And so there's some, I'd say, amplified unknowns, even with the representational model. So if your question is it too abstract or too realistic? I think you could make an argument either way. Critically, it's too much of one thing per job. For sure. Yeah.
Well, YouTube was quiet, so the fractal thing, it's like, it's very satisfying, I suppose, that you got 4/3 or whatever, but the idea that if you're simulating a landscape in a computer land, it should represent the spatial statistics of the real world, and that's a use. But like, why does it matter that wetlands are fractal, or like what's the point? Like all that work to characterize that fractality.
There's the statistical and the geometric parts of it, and the statistical to me has a more direct, clear, practical utility, where the size distribution of the wetlands. Do I expect to have a uniform distribution, an exponential distribution, a normal distribution? When some wetlands go dry, what fraction of the wetlands are going dry based on the geometry? If I lose some of the smallest wetlands, like what fraction of the, so I need to understand what's the size distribution, what's the shape. And generally speaking, we find them to be very wide distributions of sizes. And I think that would directly translate to what are the various ecosystem functions that I would expect. For example, maybe the ecosystem function that you're interested in is very distinctly related to what's the most productive part of the ecosystem is commonly right the terrestrial aquatic interface. And so maybe it's the edge of the wetland that is maybe for your case, very ecologically significant. In which case, what is the length of that interface? So now I know how many wetlands do I have, what is their size distribution based on the perimeter area ratio. And now we'll tell you about the extent and significance of that perimeter. And we can say it more accurately, I guess. Yeah. That's how those go together.
All right, well, YouTube is really quiet, so we'll give one more round of applause to Dr. Jowett. All right, so next week, keep turning in your abstracts, and you're gonna turn in 4 abstracts for Dr. Jowett. It's 4 lessons now. Next week we have our own Nicholas Chen in the back there. Oh, it's coming up quickly. Are we ready? Okay, so we've got Nick Chen presenting to us on investigating the drivers of Florida red tide. All right, till then, see you guys next week. Thanks, YouTube. Bye.